Welcome to the Explainer. Today, we're going to dig into the secret sauce that powers pretty much everything electronic in your life, from the phone in your hand to the biggest supercomputers on the planet. We're talking about parallel hardware.
So let's kick things off with a question that really gets to the heart of modern computing. You've seen the ads, right? Your new phone has an 8-core processor. But have you ever wondered why we can't just make a single core that's 8 times faster? I mean, for a long time, that's exactly what we did. Just make one processor faster and faster. But that whole era? Yeah, it's over. So what gives? Why are we stuffing all these little brains onto a single chip now?
All right, so here's our game plan. We're going to start with why we even need all this parallel speed. Then we'll look at the 2 big blueprints for making it happen. After that, we'll dive into each of those, what I'm calling the synchronized army and the independent agents. And of course, we'll cover how we connect all those cores and tackle one of the trickiest problems in parallel computing, cache coherence.
So first up, the need for parallel speed. Why do we have to change course? Well, the simple answer is we basically hit a wall, a literal physical wall made of heat and the laws of physics. For years, we were just flooring the gas pedal on a single engine, cranking up the clock speed. But you can only do that for so long before the engine just melts. Seriously. So engineers had to get creative and find a totally new way to get more power. And that new way was to go parallel.
And that solution, of course, is parallelism. Now, to be clear, when we talk about parallel hardware in this explainer, we're focusing on the stuff a programmer can actually see and use. You know, the hardware that a developer has to write code for to get that extra performance. And that's a really key point. All this incredible hardware power isn't free. It doesn't just happen. You need software that's smart enough to actually take advantage of it.
Okay, section 2. This is where things get really interesting. Once you commit to building a parallel machine, you're immediately at a fork in the road. There are 2 huge, fundamental choices you have to make right at the start, and they'll define everything about how your computer thinks. So that first big choice, it's all about how you manage the workload. Think of it this way. Are you going to have a single general barking one order to a massive synchronized army? That's SIMD, or single instruction multiple data. Or are you going to have a team of highly skilled, independent agents, each with their own mission and their own set of instructions? That's MIMD, multiple instruction multiple data. 2 totally different ways of getting things done.
And the second big choice is all about how your team communicates and shares information. Do all your workers huddle around one giant shared whiteboard? That's a shared memory system. Everyone can see and edit the same information. The alternative, everyone gets their own private notepad. To coordinate, they have to physically pass notes back and forth across a network. That's a distributed memory system. Again, a huge difference in how things operate.
All right, section 3. Let's really dig into that first model, SIMD, the synchronized army. This approach is powerful, super efficient, but as we'll see, a little inflexible. It's all about doing one simple thing, but doing it thousands, even millions of times, all at once. So here's the core concept. You have one brain, the control unit, that comes up with an instruction. Let's say, add these 2 numbers. It then broadcasts that single command out to this huge army of little calculators, or what we call data paths. And in perfect lockstep, every single one of them performs that exact same add operation on its own little piece of data. It's all about massive parallel efficiency.
And if you want to see the perfect job for a SIMD machine, this is it. A simple for loop, right? Adding one list of numbers to another. Every single step of that loop is the exact same operation, x of I plus y of I. All those little data paths can just line up and execute that add instruction in perfect unison. This kind of problem is what's known as data parallelism, and it's what SIMD was born to do.
But there's always a but, right? Here's the Achilles heel of SIMD. What happens if not everyone needs to do the same thing? In programming, we do this all the time with a simple if statement. You know, if this is true, do X. Well, for a SIMD army, this is a huge problem. The general can only bark one command. So any of the data paths, any of the soldiers that don't meet that if condition, they just have to sit there, do nothing. They're idle, wasting precious cycles and power, and that can seriously drag down performance.
So where do we see this in the real world? Well, the most famous example by far is the graphics processing unit, the GPU in your gaming PC or even your phone. Think about what a GPU does. It has to process millions of pixels on your screen, often applying the same lighting or color effect to all of them at once. That's a perfect data parallel problem. Now, it's worth noting that modern GPUs aren't pure SIMD anymore. They've borrowed some flexibility from the other camp, but this synchronized army philosophy is still at their core.
Okay, let's switch gears. Section 4. MIMD, the independent agents. If SIMD was the synchronized army, this is the complete opposite. It's all about flexibility and power, but that creates a whole new set of problems. And this design, it's almost guaranteed to be the one inside the computer, phone, or tablet you're using to watch this.
So yeah, forget the synchronized army. Think of a collection of fully independent processors, or cores. Each one has its own control unit, its own data path. It's a complete brain. They can all be running totally different programs, working on completely different chunks of data, all at their own pace. They are truly independent agents.
And these MIM systems really come in two main flavors, which map right back to our whiteboard and notepad analogy. First, you've got shared memory systems. Think of the multi-core processor in your laptop. All the cores are connected to one big pool of RAM, that shared whiteboard. Now, as the slide points out, getting to that memory might be faster for some cores than others. That's the whole UMA versus NUMA thing, but they're all sharing. The other flavor is distributed memory. This is more like a massive supercomputer or a Google server farm. It's a cluster of individual computers, each with its own private memory, all connected by a high-speed network. They're passing notes instead of using a whiteboard.
Right, Section 5. This leads us to a really critical question. If you've got all these independent brains working on a problem, they need to communicate, right? They need to coordinate. How do you actually connect them all? That's the job of the interconnection network. You can think of it as the computer's central nervous system.
And designing this nervous system is all about trade-offs. It's a classic engineering problem. At one end, you have something like a bus. Think of it like a single-lane road. It's super cheap and easy to build, but as soon as you get a few cores trying to talk at once, you get a massive traffic jam. At the other extreme, you have a crossbar. This is like having a dedicated private road from every single core to every other core. It's insanely fast, no traffic jams, but the cost to build all those switches and connections is astronomical.
So how do you actually measure how good a network is at handling all that traffic? Engineers have a really clever way of thinking about this called bisection width. Just imagine taking a giant knife and cutting your entire network of processors right down the middle into two equal halves. The bisection width is simply the number of wires, or links, that your knife just sliced through. The more links you cut, the more pathways there are for communication between the two halves, and the more powerful and less congested your network is.
And this metric perfectly shows why some designs are so much better than others. Take something like a hypercube, a really popular design for high-performance computing. For a hypercube with P processors, the bisection width is just P divided by 2. Now, why is that a big deal? Because it means that as you add more processors, the communication bandwidth of the network scales right along with it. It doesn't get bogged down. That's a huge reason why this kind of architecture is so powerful for building massive supercomputers.
Okay, our final section, and it's a big one. Let's go back to those shared memory systems, the ones with the big whiteboard that everyone can see. This setup introduces what is maybe the single biggest challenge in parallel computing, the cache coherence problem. The question is simple, but the solution is complex. How in the world do you keep everyone on the same page? Let's walk through exactly how this goes wrong. So, you have some shared data, let's call it X, and its value is 2. Core 0 needs it, so it makes a copy in its own super-fast local memory, its cache. Then Core 1 does the exact same thing. Now they both have a copy of X that says 2. But then Core 0 updates its copy. It changes X to 7. A moment later, Core 1 needs to use X. So which value does it use? Does it use its own local copy, which is now wrong, it's stale data, or does it somehow know about the new value of 7? That is the cache coherence problem in a nutshell.
So how did engineers fix this mess? Well, they came up with two really smart solutions. The first one is called snooping. It's pretty much what it sounds like. All the cores are connected to a shared bus, like a party line, and they're all constantly listening, or snooping, on that line. When one core writes a new value, it shouts it out on the bus, and all the other cores hear it and know to throw away their old stale copies. This works great for a small number of cores, but can you imagine 1,000 people on one party line? It's chaos. It just doesn't scale. For bigger systems, they use a directory-based approach. Think of it like a library checkout system. There's a central directory that keeps a list of every piece of data and which cores have a copy of it. When a value changes, the system just looks it up in the directory and sends a specific update message only to the cores that need it. No more shouting. It's much more efficient for large systems.
But even with these solutions, you can run into this really subtle, really nasty performance killer called false sharing. This is where things get weird. Imagine two cores are working on totally separate, unrelated pieces of data. They're not sharing anything. But just by bad luck, those two pieces of data happen to be stored right next to each other in memory, on the same page in the notebook, so to speak. Now, every time core 0 writes to its variable, the coherent system sees that the whole page has changed and tells core 1 to throw its copy away, even though core 1's data wasn't actually touched. They end up constantly invalidating each other's caches by accident, which creates a ton of unnecessary traffic and just kills performance.
And that really brings us to the most important takeaway from all of this. The hardware is now fundamentally parallel. Your phone, your laptop, the cloud. It's all built on these principles. The potential for incredible speed is there, but here's the kicker. That power isn't free. It's not automatic. The hardware is ready to go, but is your software? Unlocking that potential is no longer the job of the hardware engineer. It's now up to the software developer to write code that can think in parallel,